smoke, and another lungful of tar, and the desire to go on smoking. So avoid this handed molecule. It's not good news. Now, there's another effect of smoking, and that is this, that when you burn things, and you keep hearing about this these days in, say, motor car exhausts, when you partially burn things, and the burning of the cigarette here is only, in fact, partial, then you produce carbon monoxide. And the problem with carbon monoxide is that it combines with your blood, your hemoglobin, which is a giant-handed molecule, and that, the combination with your hemoglobin, prevents your blood taking up the oxygen, which is what it's for. Its job is to push oxygen around your body, and that'll be effective. Now, we can show the effect of smoking directly. Now, if I can have a volunteer, please. Yes, why, would you like to come and help me? Thank you very much indeed. Now, have you been smoking recently?
No.
No? Fine. Sit there then. You're all right? You pass? Good. Okay. Now, what we're going to do is to measure the amount of carbon monoxide. Your amount of carbon monoxide. All you want to do is take a deep breath, right, and then pop that in, and then ready, blow. All right, and this is, keep blowing. Okay. Let it all out, breath, right. All right, all the way down. That's all right. Now, he's got so little carbon monoxide in his breath, thank goodness, that our meter here, notice there's a little flashing green light there, and it's just registering. Just registering. And that is typical of a healthy, upright, non-smoking lad. Okay, jolly good. Thank you very much for coming down to help us. But, and we've persuaded Bryson, who's another healthy, upright lad, just to have a cigarette. And Bryson, will you join us and you're going to be able to show us what it's like to, what the effect of having a cigarette is before. So he's going to do exactly the same. When you take a deep breath and out through the meter, right, he's blowing steadily, right, notice, it's going up, and it's going up, and it's going up. He's still got a bit of breath going. He's going a rather peculiar shade, but that's all right. And notice how we crawl up the scale here. And that tells us he's got a lot more carbon monoxide in his blood. His blood, for the moment, is much less efficient at carrying the oxygen around than his. Thank you very much for coming to help us with that. And so all of these effects are bad for you. Smoking is bad news, both from being poisoned by handed molecules, having carcinogens, and your blood being less able to carry the oxygen about. Fine. Now let's move on. Let's move on to medicines. Now the chemicals, of all the chemicals that we take into our bodies, of course the most important, the largest amount, is food. Your food is just chemical. Can't stress that too much. But the second most important chemical that you take are medicines. And these are made in the laboratory. Perhaps the most familiar to you is aspirin. Now, aspirin is not actually a handed molecule, but most are. And they work because they are handed. And they have the property of controlling matters. Very often, our control mechanisms get slightly out of operation. Things don't go quite right. We have conditions like arthritis and high blood pressure and asthma. And all of these things can be controlled by taking chemicals in the form of medicines or drugs. And so the quality of life has been hugely improved over particularly the last 50 years by taking medicines appropriately. But one can have disasters, and disasters due to the handedness of molecules. Now, let me just show you this. Now, I don't need to stress to you the situation for those people. They were born without arms and or legs. How could that come about? Well, it came about in the 60s. These people were the victims of a drug called thalidomide, and this was prescribed for pregnant ladies because one of the symptoms of pregnancy, very common, is morning sickness. And it's very bad for morale. If you're pregnant, you've got enough to worry about anyway. And if you're sick every morning, this depresses your morale. And it was found that this drug, thalidomide, was very, very effective at curing morning sickness. But then these birth defects started to appear. And so a detailed investigation was made of all the drugs that pregnant women were taking, and it was narrowed down to thalidomide. And in spite of the fact that, as you saw on the film, these people are resourceful and adaptable, we have to make sure that that sort of thing never happens again. Now, the reason for this was the fact that thalidomide is a handed molecule. And on investigation, it turned out that the left hand of thalidomide caused the birth defect. It was the right-handed molecule which cured the morning sickness. And so it's become extremely important ever since to be able to make both hands of a handed molecule so that these can be made separately and tested separately to stop this sort of thing ever happening again. And so this has made it very important to make molecules in one-handedness only. And that's called asymmetric synthesis. Let me illustrate this. If we take a precursor molecule, okay, we're going to make this molecule into a drug. And notice the fact that it is symmetrical. I can cut that in half, and one side is the mirror image of the other side. Now, supposing I want to make that into a drug molecule, and we just have to represent that. Supposing the last stage of making our drug molecule is to add another component, another chemical component, another part of the molecule, then we can add this part of the molecule either to this side, in which case we get the right-handed molecule, or we could add it to this side, in which case we'd get the left-handed molecule. And there's nothing to decide which side would be preferred. But if we want one side only, then we must block one side. Let's just do that. Here's the chemistry. We just add a block onto there, and now this component of our molecule can only add onto that side. And there it is. We've now made our handed, in this case, a right-handed molecule. But, of course, it's not exactly the molecule that we want, because we've got to remove the block again before we get exactly what we want. And that is expensive, because it means more steps in the synthesis, and it's wasteful of material. And so what we'd really like to be able to do is to do this whole process by catalytic asymmetric synthesis. And again, we can show you that in this way. And this is another Bryson special. Here is catalytic asymmetric synthesis. And that means that we would like to be able to make right or left-handed molecules at will, right? And we would like to be able to make them continuously. We'd like to be able to choose which handedness we have, and we don't want to have to mess about with taking off blocking groups. So let me just illustrate this. Here is our same precursor molecule, exactly the same as we had here. And this is a molecular machine. This is simply a representation, but this is a molecular machine. There is our symmetrical precursor molecule. And here's the same component that we want to add selectively to one side. If we want to make a right-handed molecule, then we just put it in there. We can take out our molecule, and there it is. There's the right-handed molecule. Now, supposing we want a left-handed molecule, then we have the same precursor molecule. You can't tell the difference between those two without the balls, without the extra molecular component in place. And if we want a left-handed molecule, then we arrange it for it to come to the left side only. And there we are. So we can make, by this catalytic asymmetric synthesis, right or left-handed molecules at will. This is right at the front of commercial synthesis of this sort. Right, now let's round off this little part of the talk with a glimpse at some current work. We've been talking about all these biologically active molecules going to specific parts of the body and being detected. And let me give you a link, another link with our research in Sheffield. What we've got here is a nice gold mirror. All right, we can make that flash by putting it in the right arrangement. Yes, good. All that is a sheet of glass covered with a very, very good, smooth gold mirror. And what we've done is to stick on the surface of that gold a sticky molecule which sticks to gold very effectively, and in the surface we've got a hand. All of these molecules sticking on this surface are handed, and there are about 1,000 million of these molecules sticking on each square centimetre of this surface. And what we want to find out is, do molecules selectively stick to a surface like that? In a way, it's a very crude imitation of a membrane, but we can control that much better than we can control biological systems. And so what I want to illustrate for you is that, and we need a blow-up. See, that's really too small for us to see anything, so we're going to blow up things tremendously in scale. And here we have yet another Bryson special. What we've got here is a block of gold. Well, not really, but that is the equivalent of our gold plate. And Bryson has arranged that this block of gold will be covered with hands. Covered with hands. And so now we can imagine that we might be able to detect human molecules and the selectivity of a surface like this to human molecules. And I'm very, very lucky to have half a dozen human molecules. Will my human molecule brigade please stand up to attention? That's right. File down here, please. Now, what I want you to do is just go past this board, and I want you to use your natural hand. And shake hands with the gloves. If you get a proper handshake, then stay with it. If not, just pass on, because you're behaving like molecules flowing over a surface and seeing if you're sticking. Will you lead the way? Thank you very much. If you get a proper handshake, just pass on. Yes, and if you get a proper one, stick. So if you don't get a proper handshake, pass on. Right. Look at what we've done. This handed surface has trapped 3 charming-looking right-handed molecules. And it was the left-handed molecules that it didn't detect. Thank you very much for coming to help us. And so you can see that in a demonstration of that sort, and this is what we're trying to do with our gold mirrors in Sheffield, is to find out how selective we can be with such surfaces to pick one molecule rather than another, one hand of a molecule rather than another, because that is actually at the very basis of biological receptors. Now, we've been talking, as it happens, about small molecules all the time. We've been talking small. Well, what about talking big? And I want to introduce the handed giants. We've been talking about the handed pygmies, and now I want to talk about the handed giants. Well, how do we make giants? Well, man can make giant molecules. Nature is also very good at it, but we'll come to nature in a moment. How do we make handed giants? Well, we start off with a pygmy molecule. Here I've got some pygmy molecules. It's a tube of pygmy molecules. These are really quite small. They've only got about 20 atoms or so. And notice the fact that we've got a mobile liquid there. Okay. Full of pygmy molecules, quite small, and we want to join these together, just like a string of beads, to make a giant. So let's do that. I need a little bit of catalyst, this little bit of blue catalyst. I'll put that in like that, and shake it up well. Like that. Okay. Now we're just going to shine a bright light on it. Bryson, thank you very much. Put it in there like that. All we're doing is shining a light. I can pull it out again. We had a mobile liquid, remember before. What have we got now? We've got a solid. Okay. What has happened is that the pygmies have all joined hands, and they made a long, probably between 1,000 and 10,000 pygmies have all joined up to make giants. And that is a very, very important matter, because we talk of giant molecules of that sort. We call them polymers. You've all heard of polymers, and that word comes from poly, meaning many in Greek, and mer, meaning a part. Polymer, many parts. And that's exactly what that is. And these are very, very important. Bear in mind, the only change of property that I could show you was the fact that we were going from a liquid to a solid. And this change of property in molecules of this sort is the basis of the polymer industry. It's a huge industry. You've all heard of polyvinyl chloride, polythene, and so on. All of these polymers, these have changed the quality of your lives. Chemistry is always changing the quality of your lives over the last 50 years. The first polymers, apart from a few very specialized ones, really came on the market for the first time 50 years ago. And if you looked around your kitchen at home, you'd see a complete difference. And 1/3 of all the chemists who have ever been trained in chemistry have worked on polymers. It's a huge industry and very, very important. Now, nature makes polymers too. Man has been making polymers for roughly 50 years. Nature's been making polymers for about 3 billion years. And so she's very, very good at it. And one of the most important of polymers has as its pygmy unit glucose. We're always coming across glucose. It's a tremendously important molecule, and nature sticks glucose molecules together to make giants. Let's take a typical example. A familiar vegetable. When I cut it open, what have we got? We've got starch. That's the starch granules in this potato are the food reserve of the potato plant. When the potato in the spring starts to grow, it uses up the starch to make its stem. That is being used, and that's a giant molecule. And these food reserves, just like the breadfruit, was exactly the same thing, storing starch, which is a polymer of glucose. Now, we need glucose reserves too. But our glucose reserve is not starch, although, of course, we exploit the potato plant by pinching its food reserves, eating them ourselves, and then what we do is that the glucose that we get from that we actually make into glycogen. That's our food reserve. Now, I just need to do a little bit of dissection on Andrew. We'll just take off his rib cage so that you can see what is what. And what we've got under Andrew's rib cage is his liver. Okay, that liver is the biggest organ in the body, and about 8% of it is glycogen. That's our food reserve. And the food reserve then here has, of course, to be used. When we need exercise, then we need glucose, which is released from our energy store in the liver. That's released into our bloodstream, and then we can use it, burn up the glucose in the exercise that we take. If we run 100 yards, we use nearly all of the glucose in our blood, which is a total of about 5 grams. But then, if we run further, our liver releases glycogen. The glycogen is broken down into glucose, and we can keep on running. And so it's a very important matter for marathon runners, for example. And they eat lots of pasta, starch, make it into glycogen, and so it's ready for running. Good. Now, this business of releasing glucose into our blood and controlling the glucose concentration is very, very important. And it's policed by a giant-handed molecule called insulin. And if that policeman goes off duty, then we've got trouble, because our glucose concentration in our blood has to be controlled very carefully. And when it goes off duty, if insulin goes off duty, the policeman, then we have the condition known as diabetes. And this is a very inconvenient condition, because you've got to keep knowing how much glucose you've got in your blood so that you can then compensate by eating at the appropriate time and so on. And so the monitoring of blood glucose is a very important matter. And this is done with an instrument invented by an old friend of mine, Professor Alan Hill of the University of Oxford. Now, in order to show you how this works, we need a specialized volunteer, and I won't ask any of you to volunteer because Dr. Bryson Gore, could we have a more appropriate name for a blood donor, is going to give us not a few pints, not even an armful of his blood. He's only going to give us a mean little drop, and then we'll see what happens. Thank you very much, Bryson. You're still looking a good colour, nevertheless. And what is happening here is that we're counting down, and the way that this is working is that the glucose in Bryson's blood is being detected by a handed giant, which has been put on this little white slip that you see here, and it's sending electrical signals into this machine, and that has now told us after 30 seconds that the concentration of glucose in Bryson's blood is 3.8 millimolar. That's a typical value. The values range from about 4 to 6 or so. So he's a bit low. He's been working very hard, so it's not surprising. And this is a breakthrough in this sort of detection and has many applications and variations in detection by handed molecules of substances like glucose. So it is, in fact, it's a very important matter. Now, it's holiday time, and we've been indulging in handed giants, like turkey and so on. Protein, too much carbohydrate, and all the rest of it. And we thought it'd be rather fun to try and make a natural handed giant. And Bryson, again, here we've got, you see, he's all wearing his protective clothing and so on, and we're going to try and make you a handed giant. It is a bit of a problem. He needs to stir it up well. We can't always be quite sure that this experiment is going to work. There's always one dodgy demonstration in every lecture. Keep stirring, Bryson. It's taking a little bit of time. You may be guessing at what we're aiming for. Keep stirring and keeping that flame going. What we want to look for, of course, is the change of state, because we're turning glucose into a giant, and we've already seen what happens when we turn a pygmy into a giant. It's only going, it's going to need a little bit longer to go, and so before the lecture, we prepared this handed giant in its familiar form. This is what they do on cookery programs, of course, which these lectures are not to be confused with, and there you are. The result is the most delicious of all the giant handed molecules, toffee. We've come now into the land of the handed giants. In the next lecture, we want to invade this territory and see the behavior of these remarkable molecules. Thank you very much.